everyone. I'm Sravya. I'm going to give a presentation on agent goal management using goal operations. This research is supported by NSF and ONR grants. So, yeah. Here's how the next few slides are organized. First, I'm going to introduce you to intelligent autonomous agents, and then I'll talk about our approaches in achieving an intelligent autonomous agent. And then I'll explain about the problem domain and walk through the working example and present you the empirical results that we got, and finally conclude my talk. So any agent that can perceive the environment around it to gather information and process the information to generate some thoughts and maybe act on some of those thoughts to achieve them in the real world, and then also able to communicate its own thought processes to other agents in the real world can be termed as an intelligent autonomous agent. And if we want to achieve or build such an agent, then there are several issues that we might encounter. And two of the major issues are unexpected events in the real world and also the issues with partial observability. And some of the examples of such intelligent agents are Waymo, self-driving car, and also humanoid robots such as Simon. So out of all the four major capabilities, we focus on the thinking part most. And even in the thinking part specifically, we deal with goal management. And there are several approaches in theory to achieve goal management. But we focus on an approach using goal operations. So we have identified some goal operations, and out of several goal operations, we mainly focus on three in this research. The first one is selection, meaning let's say an agent has a bunch of goals that it can achieve, which one to select first, and how can it order its goals, and something like that. And goal change. So since our agent will most probably be working on a dynamic environment, how is it going to change its goal if the conditions in the environment change? And also, goal formulation, meaning let's say there's no human expert or any other agents available to help the agent. In an anomalous event, it should be able to come up with its own goal to help itself. Right? So again, we have a bunch other goal operations, but we focus on these three. And even between these three, we especially focus on the situations when multiple of these operations are relevant, meaning what would happen or how can an agent make a choice when multiple of these goal operations co-occur. So we have implemented each of the goal operations in a general purpose cognitive architecture called MIDCA, Metacognitive Integrated Dual Cycle Architecture. And MIDCA majorly has two cycles of operation, the cognitive cycle and the metacognitive cycle. And each of the cycles have 6 individual modules, and each of the 6 individual modules perform certain different operations on their own. And we have referenced cognitive architecture MIDCA in our paper. Please feel free to look at it. So here I'm going to present a demo with Baxter working on tic-tac-toe. So Baxter is a humanoid robot. It works with ROS, Robot Operating System. It has 2 arms with 7 degrees of freedom each, and it has a sonar sensor around its head. And it has 3 inbuilt cameras, 2 on its arms, 1 on its head. And we have mounted an external camera, ACS Xeon, around its waist, somewhere right over here. And we do object detection using the regular deep learning algorithm, CNN, and transfer learning. So in the tic-tac-toe domain, the agent has 3 main goals. The goal to either win, lose, or draw. So obviously, if it were a smart agent, it's going to pick to win. The agent is O, and it is going to play tic-tac-toe with a human person, and the other person would be X. And that's me, by the way. And so it continuously perceives the world and tries to act according to the world. And the initial goal it's selected is to win the game. So right about here, it would recognize that it can no longer win the game. So instead of just stopping abruptly, it would change its goal to the best possible goal and choose draw instead of winning, and it would still continue to play the game instead of just getting stuck or not doing anything. So it successfully completed the game. So this is the demo with just one, each of the goal operations kind of implemented individually. And but in our research paper, we are trying to address a scenario where multiple of these goal operations are relevant, meaning let's say if the agent is trying to select on a goal and then a fire occurs in a room beside it, what is it going to do? Should it prioritize selection or should it prioritize formulation and so on? So to address this research problem, we first started out with assumptions. We are only going to consider the situations when anomalies occur, and even in that, we only consider the anomalies that affect the agent negatively, meaning there could be some unexpected events in the world that might help the agent by maybe giving it more information or something. So we are not going to consider positive anomalies. We are only going to focus on the negative ones. And so after considering these two main assumptions, we came up with three factors that might help the agent determine or pick one goal operation at a time. So those three factors are negative effects of the anomaly on the agent, and how can the agent know the priority of its goal that it's working on, and also the amount of resources that are available to the agent. So among these three, let's talk about one at a time. So the first one is negative effects of anomaly on the agent. So we have further subclassified this into three more factors. The first one is analyzing how an anomaly is affecting the agent's goal negatively. So for this, we are mostly relying on a human expert with a knowledge base. And if an anomaly occurs for the very first time, then it would automatically start with high priority. And then after looking at the situation, after dealing with the anomaly once, it would create a case and then put it in the knowledge base. And the second subfactor is estimate of how many times the anomaly repeats. So let's say if an anomaly is really minor, but it kind of occurs over and over again, then the agent might have to deal with it in the long run. So for now, we are assuming that the anomalous events are independent. So we have used Poisson distribution to model the repetition factor. And after we model and kind of get the numerical values from the Poisson distribution, we later qualitatively divide them with a threshold value of high or low. And then the third subfactor is negative effects on agent's health itself, meaning its battery life or its physical damage or something like that. And we have designed a custom cumulative function. Again, we have defined this one in the paper. Please feel free to look at it. Again, the numerical values that we get from the cumulative we have divided them into qualitative factors again of high or low. And for goal priority, we are using inspired by Dr. Raja Shank's work, and we are just trying to implement the goal types from his book, Scripts, Plans, Goals, and Understanding. So currently we have three types of goals: crisis goals, preservation goals, and achievement goals. And we prioritize crisis first over preservation over achievement. And then for estimating the resource availability, we are once again using a simple knapsack algorithm. And if the agent is able to achieve 85% of its entire set of goals, then we classify that the resources would be sufficient. If not, then we say no. Um, so we then combine all of these factors and then generate human return rules in our Midka. And based on all of the qualitative values that it got, and it would just do a rule matching algorithm, and then it would pick a right goal operation at the right time. Um, so again, please feel free to look at the paper. Uh, okay, thank you. Um, we have implemented our work in a real world domain, which is kind of simulating Grace Reef National Marine Sanctuary area off of Georgia's coast. And this is the area kind of zoomed in, and this is the research only area, this is the regular area. And in the research area, we've just taken part of the land and kind of built a simulator using Moose, mission oriented operating suite. And on the left hand side is Grace, which is our robot. And the shaded area around it is its sensor radius, and the little red dots are the fish tags. There are a bunch of fish that are tagged and are left in the water area right over there. And these red lines along the edges are obstacles, meaning the obstacles that the agent cannot pass through, even if it gathers more information. And the green lines along the edges are obstacles again, but if the agent kind of formulates a goal and kind of gets more information about them, it can either dive up or like dive down and then pass through the obstacle. And yeah. So this is the generic overview of the domain for now. And these are the robots. On the left-hand side are the robots that look like fish from Michigan State University. And on the right-hand side are the Slocum gliders from Georgia Tech and also University of Georgia. And this is the research vessel. And yeah. So in the domain, again, the gliders have a bunch of sensors to gather information like temperature sensor, salinity sensor, pressure, and so on. So the major goals are to discover hotspots in the area. Again, hotspots are the areas where there is bigger concentration of fish, and also possibly track movement of the fish. And the potential problems that occur in this domain are remora attacks, meaning those are sucker type fish that come and like latch onto the gliders and hinder the movement of the gliders. And there's blowout situations, meaning tides would just blow out the robot off its course. And obstacles, again, obviously coral reefs and something that hinder the movement of the agent. And shark attacks, although they happen very rarely, they do, and we do not have a solution for them yet. Um, a quick working example on this one. So here is our robot. We have divided the area into 25 cells, 5 by 5. And this one and this one could be potentially termed as a hotspot because there's high concentration of fish tags there. And the agent has the goals to kind of survey each of these 25 cells. And the agent needs to select among the 25 cells. So it has selected the one that it's currently at. And right over there, it encountered an anomaly. So it would now be left with the decision of would it continue with the selection or would it formulate a new goal to address this anomaly. So thinking that it's not a huge threat to its health, it wouldn't. It would just prioritize selection over formulation, and it would select another goal. And the long pause right over there is a remora attack. So yeah. So it has selected the second area, and it has now once again encountered the anomaly again. So now thinking that the anomaly occurrence is much more frequent, it now tries to address the anomaly by trying to gather more information about the obstacle. So hence the straight line survey kind of thingy. And again, the long pauses in between are Remora attacks. And so right over here, once again, it sees that there's an obstacle, so it prioritizes formulation over selection again. And after seeing that it can go through the anomaly, it kind of goes in and tries to achieve the goal. And yeah, and so we've generated 1,000 fish tags in the simulated environment, and the time limit to survey all of the cells is 600 time units. And we have randomized the initial starting location of the agent. And again, anomalies, we have tried to simulate remora attacks, blockades, as well as flow anomalies the best that we can in the simulator. And the metric that we have used is percentage of goals achieved, meaning out of 25 cells, how many was it able to achieve. And the agents for comparison, baseline, meaning the agent that would only try to achieve the goals that it was given, and it would not try to tackle any anomalies at all. So that is our lower bound. And random agent, which chooses goal operations in random. And then smart agent, the one that uses the algorithm that we have developed. And ideal agent, again, it is the upper bound agent, and it is the agent working in ideal environment, meaning the environment where nothing goes out of the plan. So here are the results that we got. On the x-axis is the time, on the y-axis is the percentage of goals achieved. Our baseline agent is right at the bottom, and our ideal agent is the red one, and our smart agent is the green one, which, although it takes a little bit of time, it eventually matches the performance of the ideal agent. And then our random agent, although it does make some nice choices randomly, it also makes some bad choices in the way. So it eventually flatlines. And again, the flatline performance is achieved because the Remora attacks are incremental in nature, meaning once a Remora attacks, and if the agent doesn't deal with it, then another Remora attacks, and so on. And it would eventually, the agent would no longer be able to move, kind of thing. So, and so again, in conclusion, our research is mostly in preliminary stages, and it's really hard to combine the intelligent algorithms with the control architectures. And we believe work on belief spaces would better integrate these two. And we have our open source code available on the GitHub link. And for the future, we would like to include many other goal operations, such as delegation and goal sharing. And we would also want to improve the diversity of the qualitative factors that we have considered. It's not just high or low, maybe high, medium, or low, and something like that. And again, we believe working on belief spaces further is going to integrate the control architectures with cognitive architectures much more concretely. So, yeah, uh, thank you. Any questions? Yes, Pat? Uh-huh.
It's like, well, hey, if I don't have any goals,
Mhm.
then it's going to be very easy for me to satisfy them. So I'll be very, very happy, right? So there must be some meta level approach to evaluating. I don't know what it is because I've been worried about it too.
Uh-huh.
But so when you measured the goals that were achieved, were those self-generated goals or
Uh-huh.
those goals that were there at the beginning?
Uh-huh. Uh-huh.
Which was
Oh,
it?
the goals that were there at the beginning,
Aha.
all the 25, that's all.
But
Yeah,
you could imagine
yeah.
that it should care about the goals that it generates itself too. So
Mm-hmm, mm-hmm,
I'm not expecting a detailed answer, but
mm-hmm, mm-hmm,
it seems to me like it's worth thinking about.
mm-hmm. Yeah, yeah, sure.
Who's next?
Why the constraint is similar?
Because you don't want to let go of the original goal. You want to kind of achieve it. I mean, that's how we are currently defining change for now. So we might change it in the future, but
Please, when you ask a question, wait for the microphone. Otherwise, online, your question will not be heard. Thank you.
So in this work, we know there's a number of things that could be learned from this. For instance, you use a straight 85% on the resource allocation. That might be better to be another number. But have you ever thought about how you might learn a new goal operation itself? What would be worthwhile there? Is that something that's subject to learning or no?
That's a good question. I know that the factors are subject to learning and they can be improved, but learning a new goal operation on itself might be a meta level task and it might need more thinking from my part.
Any other questions?
So in your task, there is a specific time restriction on completing the survey. Do you observe that the same kind of anomaly, like hitting into a barrier or one of these attacks, changes the behavior, whether it's in the beginning or towards the end of that time period, and how so?
So if the agent is kind of at the end of the goal, then so let's say a Remora attacks, then it would prioritize the Remora attack lesser and it would continue with the surveying of the cell. But if it were in the beginning, it's going to spend much more time on the Remora attack.
How do the remoras latch on to the vessel?
They have suckers. I think it's a joke. Okay. Yeah. Thank you.
And then there's one online question from Stephen Jones. Is that the one you? I'd love to hear more detail about how where the method for selecting the goal operator is implemented in or among the MIDCA modules.
Yes, it is. It is implemented in MIDCA, and we use a simple cost to benefit analysis to implement selection, and also we use hill climbing type algorithm for some, and again there are 2 to 3 different methods by which we perform selection. Again, they are referenced in the paper. If not, I'll be happy to talk to you about that. Thank you.